Hi, everybody, and welcome back to MTED 110. Today we're going to be doing Chapter 2, starting Chapter 2. This is Lecture 2A, and this chapter is actually one of my favorite chapters because it's all about numeration systems. And one of the reasons I like it is because oftentimes if you find a student struggling with an algebraic problem or an algebraic concept in the future, a lot of the times it has to do with their understanding of our numeration system, that it's not complete enough. So let me go ahead and pull up the slides and let's get started. This lecture is going to be a little bit long because there's a lot of really, really important concepts in this chapter, and this chapter is foundational for the rest of the course, I would say. It's kind of funny because students tend to have a love and hate relationship with it, meaning some students really, really love this chapter and some students really, really hate it, but it is one of the most important ones. Okay, so the motivating question here is this. What's the difference between a number and a numeral? So just go ahead and pause for a minute and think about that. Okay, and then go ahead and talk out loud to yourself or to your group members about that. Okay, so let's go ahead and see what the difference is between a number and a numeral. So by definition, a number is the value of a quantity or a quantity, one of those two things. But a numeral is a symbol used to represent a number. So this is the key difference between these two things. A number is an actual quantity in and of itself. That's what a number is. A numeral is just a symbol that we use to represent a number. And so this ties into the whole idea of math being a language and what I was saying earlier about how we use this language to describe ideas. And if you can't make that distinction, then a lot of the stuff becomes really confusing later on. And what'll happen is students will get really, really locked into the numerals themselves and moving those symbols around using all sorts of algorithms, but they're not actually doing the mathematics involved. Like they don't really understand the mathematics that are going on because they're not thinking about the numbers. They're only looking at the numerals. The other thing is, I think I say this on a slide in a minute here, but people often don't realize how they conflate and stitch together the concept of numbers and numerals. The key point here is that a number is not the same as a numeral, and a numeral is not the same as a number. A numeral is a representation of a number. That's the key idea. So this is kind of the motivating idea right here. There's a profound distinction between the number 10 and the numeral 10. So notice here I actually took the time to write out the English spelling of the word 10 because here I'm talking about the number 10 and here I'm using this numeral 10 to represent the number 10. That's a numeral, so that's the difference, right? Um, it's often difficult for people to comprehend that they conflate numbers and numerals, and you'll see what I mean when we start looking at different based numeration systems. Because when you start doing arithmetic and representing numbers in those numeration systems, it'll really reveal just how much you stitch together numbers and numerals, as we'll see. Just keep in mind that math is a language used to describe ideas, and that language is just a system of symbols, and the ideas exist outside of that language. That's what we want to develop in our students. We want them to be able to look at what they see in their own reality and in their own existence and describe it using this really, really powerful tool, mathematics. So we have to give them that ability, that language. Yeah, there you go. We represent these ideas and interactions between them using symbols. So that's what those symbols represent. Just to give you an example, if I write something like this, 2 plus 3 equals 5, that's a mathematical sentence. And what I'm doing is I'm using these various symbols that you see in this equation to talk about concepts and how they're related. In this case, the concepts are pretty rudimentary, but I think you'd agree they're absolutely fundamentally important to understanding things, right? This symbol right here is just the symbol I'm using to represent the concept of the number 2. So 2, you can think about 2 of these, or you could think about, for example, even 2 linking cubes. Oop, dropped half of them. 2 linking cubes, for example. I'm thinking about this. And when I write this symbol down right here, that's what I mean when I use that symbol, that concept of 2. The same thing for this other symbol here, the symbol for 3. That's just a symbol I'm using to represent the quantity 3. So here you go. Here are 3 objects. right there. There's 3 linking cubes, right? That's what that symbol 3 represents. And then the same thing with the symbol 5 over here, the numeral that we use for the number 5. And then we've got these interconnecting things, right? And it's really cute because you could imagine it like this. These things right here, these are the verbs. Those are the verbs in the sentence. And the other things, the other things, these things right here, those are the nouns. And so we've got nouns and we've got verbs and we're combining them to make sentences. And in this case, the sentence says 2 plus 3 is equal to 5. That's what that sentence says. But that's the idea. So these are just symbols used to represent ideas and their relationships between them. And this particular chapter is all about these symbols right here, these numerals, and how those represent numbers and how we represent numbers with those numerals. Okay, so yeah, this distinction is important to keep in mind with young learners because what you might find is that students are actually very, sorry, your student might have a great deal of numeracy, meaning the ability to work with numbers, but they might have trouble with the numerals representing them or how the algorithms work. And we'll see that later on in some videos even. Okay, so let's get started here. A numeration system is just a system that expresses quantities using numerals. So that's what it is. We use the Hindu-Arabic numeration system, which is a place value system. And these things right here, these 10 symbols are called the digits. We call them digits. Maybe because we actually have 10 digits ourselves, right? And that makes sense. Like, why do we actually count by tens? Well, it's pretty natural for us to count by tens. Um, but yeah, so this is a system that originated in India back in, I think, the 6th or 7th century. I can't remember off the top of my head. And what's really amazing about this is that we can represent any number with just these 10 symbols. That's all we need is those 10 symbols and a decimal point. Or actually, I really should call it a radix, because that's what that point is. You're not always going to be in the decimal system. You might be in other systems too. Okay. So here's what's interesting. By comparison, the Parahya people of the Amazon, they use a numeration system that has no words to describe anything other than a small amount and a large amount. So they don't distinguish between 2 and 3 and 4 or 10. They just know a little bit and a lot. And that's the whole numeration system. Very, very different from ours, but it is still a system of counting. It's a numeration system. The Luo people of Kenya, they use a quinary system, which is base 5. So they count by fives. And again, that's not too unnatural if you think about how many fingers we have on each hand. It's just that if you were to use these symbols in base 5, some of those symbols won't exist in base 5. Because if you're counting by fives, then you're going to start grouping by powers of 5, as we'll see in a minute here. Okay, so just to hammer the point home that these are that these are just representations and not the numbers themselves, here's some different representations of the number 12. So here it is in Old Chinese, and that's just the number 12. So there, when you see that symbol, they're talking about the quantity 12, 12 objects, 12 pencils, 12 linking cubes, 12 sheep, 12 anything. And then this is what it is in Greek. Right? And then this one, I think a lot of you have probably seen, right? Roman numerals. Everybody had to learn Roman numerals when they were back in elementary school, I'm sure, right? There you go. Roman numerals, that's the number 12. That's how you write the number 12 in Roman numerals. Notice those are not Hindu-Arabic numerals, those are Roman numerals. And then there's some others, right? Here's Babylonian. Maybe you can even see where the 12 comes from, right? Maybe this little guy right here, maybe that's really representing 10, and this is representing 2. And if you add those two things up, you would get 12, right? Pretty interesting, right? Same thing with the Mayans. So Mayans, maybe you can see where 12 is represented in that symbol, and so on and so on. Now, oops, pop that back in there. So this is how we write 12 in base 10 in our decimal system. But what's interesting is right at the end here, that's also the number 12, written in base 4. And this is right where your brain should kind of like start to you start to wonder about what's going on there. Well, this is a good time to just pause and have a think, right? That's the number 12. That's the number 12, but it looks like it's the number 30. It looks like it's the number 30, but it's the number 12? What? What's going on? What's going on, right? Well, we're going to talk about that right now. So this is the indication. So if your brain breaks when you see this and I say that's 12, that's because you automatically associate numerals with numbers, which makes sense because we've been training you in the decimal system since you were a kid. Okay, so let's talk about our decimal system and let's make sense of it before we start getting into some other decimal or other systems. So our decimal system is base 10 because there are 10 digits. It's a place value system. So a place value system means that we group quantities by powers of 10. That's literally what it means. So this is the idea. Whenever you hear base 10 or base anything, that's what it means. It means we group quantities by powers of that number, and each position in a numeral gives the quantity of a specific power of 10. So this harkens all the way back to when you first learned this stuff back in first grade and kindergarten, right? This is the ones place. You might remember this, the ones place. This is the tens place. This is the hundreds place, and so on, right? And then over here on the other side of the decimal point, or the radix, you could call it, if it's not base, if it's some arbitrary base, we call it a radix, radix. Maybe I could write that a little bigger. radix. And then the next column are the tenths, and then the hundredths, and then the thousandths, and so on and so on. And whenever we or whenever we describe a number, like let's say we want to describe the number 18.3 or something like that, that's a quantity, right? I've got 18 objects and then I've got 0.3 of another object. Well, what we do is we group by powers of 10. How many tens do you have? Well, in the quantity 18, there's only one whole 10. So we write the number, or we put the numeral 1 right here in the tens place to indicate that there's one group of 10. And then how many little bits are left over? We have 8 more things, right? Well, that's not enough to make another whole 10. So we write it right here. There are 8 ones, and that's why that symbol 8 goes in the ones place. And then 18.3, well, 0.3, that's not even enough to get a whole 1. So instead what we did was we have to put it over here in the tenths place, the tenths place. And that's the idea. That's the whole idea right there. So if you can wrap your head around that, it's going to make things a lot easier because now, or I shouldn't say now, but later what we're going to see is that these places don't have to hold, or sorry, don't have to count powers of just 10. They can count by powers of 2, 4, pi, square root of 10, square root of 11, any numbers you want really, positive real numbers. So let's go on here. Let's look at this number here, 2,357. The number 2,357 is represented like this: a 2 in the thousands place, a 3 in the hundreds place, a 5 in the tens place, a 7 in the ones place, and then there's nothing else beyond that. So sometimes we'll put a 0 after the decimal point. And what that's really saying is this. We're saying we have 2 groups of 10 cubed. So notice that 10 cubed is 1,000. Right? So in this quantity, 2,357, we're saying you have 2 groups of 1,000, and they're represented right here. 2 groups of 1,000. Actually, let me use a different color to, there we go, I'll use this. There's our 2 groups of 1,000 right there. And that's why we say there's 2, and then we have this little power of 10, 10 cubed, which is 1,000. All right, then we move on. Over here we have 3 groups of 10 squared, but 10 squared is 100. Right? 10 squared equals 100. That's why right here we're saying there are 3 hundreds, 3 of those hundreds. And let's keep moving along here. Now we're talking about 5 tens. 10 to the 1 is just 10, right? There we go. So we're saying we have 5 of those tens. And then last but not least, we've got 7 10 to the zeros. But 10 to the 0 is just equal to 1. That's one of those properties of exponents that you should know for this class. If you'd like, I can prove it. It's a very easy proof and it's kind of cute. Just ask and I'll do it in the collaboration meeting. Now, Where was I? Oh yeah, there. Okay, so that's why we have 7 1s right there. And so that's pretty much how our numeration system works. Those digits literally map to these places, just like that. Yep, I'll do that. And those places are determined by these powers right here. These powers, 10 cubed, 10 squared, 10 to the 1, 10 to the 0, and then off in that direction, and then also off in the other direction too. That's what we're doing. So that's how we count things. That's how we group things with our decimal system. All right. Yeah, but as we saw, this is not the only type of numeration system. So we have to look at some of these other ones to get a better perspective of our own and why writing things with this system may not be just the end all be all way of writing numbers down, right? So let's take, for example, Egypt back in 3400 BCE. They had an additive system to their numeration system, kind of like ours. Actually, I forgot to emphasize that back here. Let's go back for just a minute. Um, Notice here that we were talking about these different groups, 2 groups of 1,000, 3 groups of 100, 5 groups of 10, 7 groups of 1, right? Well, this counts the, oops, this counts the thousands, this counts the hundreds, that counts the tens, and that counts the ones. And then what we do is we add all of those together. And when you add all of those together, you get the quantity that we're describing, 2,357. That's exactly what's going on. So uh, Egypt's system was also additive. So they would basically have some symbols to represent some number, and they'd have some other symbols to represent some other number. And if they put them near each other, you would be adding them together and building up a representation to describe this number. We'll see more in just a second here. Their numerals were also written in order from left to right. Actually, wait, okay, wait, for you guys, it's from left to right and from top to bottom. Okay, that one's not flipped, right? Um, they also used a base 10 system, so they grouped by tens, so that's very familiar to us, but theirs wasn't a place value system. So they didn't have a bunch of slots, essentially, with a decimal or, yeah, a decimal point, and then these slots, and you would basically fill in these slots, and depending on which point you were in that sequence, would tell you how much of a certain amount you had. They didn't do that at all. So they didn't have this. So you can basically erase that from your memory for now. This is what they would use instead. So they had some symbols, which are listed down here. Here are their symbols. So for the quantity 1, they would just use a vertical staff, which we do essentially, right? For the quantity 10, they would use this little heel bone. They'd use a heel bone. For the quantity 100, they would use a scroll. For the quantity 1,000, they would use a lotus flower. So if they wanted to write the number 1,000, they would draw a lotus flower. If they wanted to write the number 1,100 or 1,100, they would draw a scroll and a lotus flower. And if those two things are near each other, it's additive, and so you add those two quantities up. Very familiar, right? That's what we do. And then so on and so on. So this is what they would use for 10,000. They would use a polywog for 100,000. A polywog is just another name for a tadpole for all of you Stranger Things fans. They talk about that in, I think, the second season. And then for a million, which is 10 to the 6, they would use an astonished man, right? Because that's what you do when you make your first million. No, just kidding. But yeah, so 10 to the 6th is 1 million. Oh, what am I doing? 1 million. I think I have way too many. Oh, no, I don't. There we go. 10 to the 6th is 1 million. So that's the idea. And over here is another example. Let me erase some of this stuff really quick. Over here is an example of the number 276. So down here at the bottom, this is how we would write the number 276. 276 in that specific order. But the way that the Egyptians would write it is right above there. They would write it like this. And if you kind of look at it, you can see how that makes sense, because look at the pieces, right? You've got 2 scrolls. Well, the scrolls represent the quantity 100. So there's 2 of those. There's 200s. Then we've got, oh, there we go. We've got how many? 1, 2, 3, 4, 5, 6, 7 of those heel bones. But remember, a heel bone is 10. So that's 70. And then last but not least, you would have these 6 little staffs, vertical staffs, right, for the number 1. And if you put all those near each other, and that means you add them all together and you get 276. Okay. Oh yeah, so they also had the ability to write unit fractions. So this is a unit fraction. For us, this would be the number, this would be the number 1/3. So we would write that we would call the number 1/3, but they would write it like above. They would write it like this. So this mouth symbol, which is right at the top, this symbol right here is a mouth, and that meant apart. And then you put it above these other symbols down here, the three staffs, and how many of those are tells you what the denominator of your fraction is going to be. That's 1/3. So you can kind of see there's a similar structure, right? It's kind of like 1/3. We do something kind of like that. We just use a different symbol for 1, and we just use a different symbol for 3, and we use a different symbol to represent a fraction. But we're still talking about the same number. That's the important part. We're still talking about the same number. Okay, Babylonia also had a different system back in 1900 BCE, but they had a base 60 system that's sexagesimal. They would group by 60s. So they had 60 symbols to represent the first numbers 0 through 59, and then they would roll over at that point. I'll show you an example here. They did have a place value system. So depending on which order you wrote things, right, it would change the quantity that you were describing. So they did have a place value system and so on and so on. So here's an example. Here's how they would write the number 4,871. That's this right here. That is how you write 4,871 in Babylonian. Okay, so let's kind of break it down and look at it and see how it compares to our system. So first, this bit on the edge, or on the far right, I should say, that represents the quantity 11. Maybe you can kind of see where that comes from if you start comparing it to this next quantity right here. Notice that also down here at the bottom, it says big space, big space. We're going to talk about that in a minute. But after you have a big space, then you scoot over and then you say, okay, I've got 21 groups of 60. So this would be like the second place in their system. So here's the first place, here's the next place, and then the next place up. And here they've got 21 of these groups of 60. So they have 60 objects and they've got 21 groups of that. So that's why this would be kind of like writing 21 right there. But we're not going to do that because that gets really weird, as you'll see. And then you do another big space. You do another big space. And then because we're counting in groups of powers of 60, this next thing says that you've got one group of 60 squared. 60 squared. So remember how in our system, the decimal system, we were going up by powers of 10, right? It was like, 10 to the 0, 10 to the 1, 10 squared, 10 cubed, 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th, and so on. Same thing with them, except they're going 60 to the 0, 60 to the 1, 60 squared, 60 cubed, 60 to the 4th, 60 to the 5th, 60 to the 6th. That's what they're doing. So that's why these are like 60 squared. This is more like 60 to the 1. And this, they don't actually say it right here, but this is basically times 60 to the 0. And that's how they would count, which is very similar to us, except in base 60. And then down here at the very bottom, I have the expanded form written in the way that we would write it. So here's 11 times 1, 21 times 60, and 1 times 60 squared, right? Add all those together, and then you get the quantity 4,871 as we would write it. Interesting, huh? Okay. Um, yeah, so here's a good question. What do we group by 60s? Because you might think it's kind of weird to group things by 60s, right? Like, uh, I don't know, that's a big number. But what do we group by 60s? It's a good time to pause and think about it. What do we group by 60s? What do we group by 60s? Not sure. Okay, so now that you've thought about it, talk out loud to yourself or your group members and tell them what you think. What did you think about? Remember, you can talk out loud to yourself too. It helps you think. Okay, so let's talk about it. What do we group by 60s? Honestly, the first thing that comes to my mind is how many seconds are in a minute? 60 seconds. 60 seconds in a minute. How many minutes are in an hour? 60 minutes. 60 minutes in an hour. And so you realize we actually do count some things by 60s. Also, think about degrees, right? 360 degrees in a full circle if you're using degrees, and you can basically add up a bunch of groups of 60. There's lots of things that we group by 60, so it's not that far-fetched to do that. But there was one issue, and the issue was this. The system could be confusing because, blank slide there. Think about this big space. What does that mean, big space? I mean, everybody writes a little bit differently, right? So if I say big space, that big space for me might be like this big for me, but maybe it's only that big for you. And what if we don't know whose space is the right width, and that's going to mess up how many things we're talking about, right? Right? Well, let's find out. Um, yeah, definitely, it could be confusing. So what the Babylonians did was they introduced a symbol as a placeholder for missing values, i.e. 0. So the Babylonians were actually the first people to invent the concept of 0. They didn't think of it as a number though. So at this point in history, way back at this point, 1900 BCE, 0 was not considered a number at all. It was not considered a number at all. It was just considered a placeholder. And what they would do is this. So here's a perfect example. This symbol right here is what they came up with for the placeholder 0. And it was essentially this symbol right here, kind of tilted on its side. Oops, sorry, tilted on its side. So it looks like this. There we go. And this whole little depiction here shows you why it could be confusing. So let's go ahead and take a look at what's going on right here. Right here on the top, these are the Babylonian numbers. Oops, sorry. These are the Babylonian numbers without 0 and the modern numbers written right below. So this is the quantity 1. This is the quantity 61. And this is the quantity 3601. You see the problem? The problem is that these last two look essentially identical. In fact, they basically are identical, right? Those symbols look identical, but they're supposed to be describing different quantities. They're describing different quantities, and that's the rub. That's the problem right there. So what did they have to do? They had to find a way to distinguish between 61 and 3,601. And you can kind of see the dilemma, right? Because what if you say, oh, I'm going to sell you 3,601 sheep, or let's say you're going to buy 3,601 sheep, and then somebody shows up with only 61, it's probably going to be a problem there. So they introduced this new symbol, 0, and now we can highlight the other right here. There we go. There we go. So just like before, this is the quantity 1. This is the quantity 61, because this right here tells me that I've got one group of 60. One group of 60. And then over here, this is 3,000 or 3,601, because this is saying that I have no 60s. But then I have one group of 60 squared, which is 3,600. Let me write that out down below here. Essentially, you've got staff times 60 squared plus 0 times 60 to the 1 plus staff times 60 to the 0. Well, 60 squared is 3,600. And then 0 times 60 is 0. And then 1 times 1 is 1. So you get 3,601, just like that. So the Babylonians were the ones who came up with 0 in that kind of capacity, and that was very, very helpful. Okay, so now let's go back and look at our place value, our decimal place value system, and make even more sense of it. So this representation over here on the right-hand side of the equation is called the expanded form. So if I ever tell you to write it in expanded form, or it asks you to do that on the activities, it says write it in expanded form, that's what it means. And like I said earlier, we can represent any number, any quantity, using only those 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, these ones right here. And remember, those are just symbols representing the quantities 0 through 9. That's all that they are. Also recall that 10 to the 0 is equal to 1. All right, so now we got to talk about base 10 blocks. Base 10 blocks are a manipulative that we use to help young learners understand our base 10 numeration system. And I've got an example here that we'll see in just a second. I have the physical manipulative, And this one's nice because you can actually just draw these manipulatives pretty well. I think Toy Theater also has one, but I'm not requiring you to use Toy Theater for this one because I think it's easy enough just to use drawings in this case. Um, but let me go ahead and try this. So let's try 2,357. Let me write that here. Let's model the quantity 2,357 using base 10 blocks. We already saw how that was split up. It's 2 times 1,000 plus 3 times, plus 3 times 100 plus 5 times 10 plus 7 times 1. All right, so here's what the manipulatives look like. I'm going to switch to just the camera for a minute here. What we've got is this. We start off with these very, very tiny cubes, and these tiny cubes represent the unit. They're the smallest thing that we're going to be able to break apart. This thing right here is the unit. In our case, we're going to let this represent the quantity 1, and hence the name unit, right? Now, if you end up collecting 10 of these units, you get a whole bunch of these little units together, you get a group of 10 of them, what you do is you can trade them in for a long. And a long is basically a stick where you've glued together 10 of those little units. And that that represents the number 10, all right? And now you can imagine what goes on next. You start to collect more of these longs, like so. I've got 2 of them. That's 20, that's 30, that's 40. The walls, wait, to 40, wait, 50. And you collect 10 of those, and what you end up with is what we call a flat. You end up with a flat. You take 10 of these longs, these little rectangular pieces, and 10 of these fit inside of here. And how much is 10 tens? If I had 10 tens, how much is it? 100. So this flat represents the quantity 100, and that's it. Okay, so now we have a way of physically representing 100. We have a way of physically representing 10. We have a way of physically representing 1. And then you can probably go on to the next step, right? What happens when you collect these? Here's 100, 200. Whoa, almost dropped that one. 200, 300, 400, 500. And you get 10 of these. And how much do you get when you have 10 hundreds? Well, when you get to 10 hundreds, you get what we normally call 1,000. You get this big cube, which represents 1,000. Whoa, it's too big, right? So literally 10 of these flats, you group them all together and you can trade them in for 1,000. And that's what this is. So what's nice is if you want to represent quantities using these, you can have it shown, or sorry, you can provide students with a physical representation of these quantities. And remember what I was saying in the previous lectures about how it's hard to go from like a story problem directly to the mathematical sentence without that intermediate model. This is exactly that right here. This is exactly that. We talk to children about numbers from birth. We talk about quantities like 4, 5, 6, 100, 1,000. We talk to them about infinity, or even early on, right? Well, it's going to be hard for them to understand that we write the number 3 by using that symbol 3. Wait, is that 3? I can't tell. Bad number to choose, right? Here is 0. There you go. That's a good one. Without giving them a model. And we say that, oh, you can represent 1,000 with this big block. Okay, so let me go ahead and draw a picture of that here. So for example, this would be 2,000. Sorry, this one's kind of bent out of shape. But here's 2,000. 2 of these blocks. Each one of them is 1,000. Here's 2,000. Nice. Got our hundreds, got our tens. Sorry, I'll show this side. Hundreds, our tens, our ones, we've got it all. So here's how we would show that with pictures. Let me go back to the slides here. And let's go ahead and represent this with base 10 blocks. And also, if you've never learned how to draw a cube, this will be the class where you get to. I'll show you how to do it right now because we're going to need 2 cubes to start off with. Here we go. So I need to draw 2 cubes, and the way you can draw a cube is to first draw a square, and then you just draw these 3 diagonal lines that are all the same length, and then connect them. And I'm just going to emphasize that this is representing 1,000. Then I'm going to draw another cube. Okay, so this is the quantity 2,000. Or if you wanted, you could view it as 2 times 10 cubed. Incidentally, that's why we call it cubed when you have a power of 3, because it basically is a third-dimensional object, and we use cubes a lot of times to measure three-dimensional objects. Okay, so we've got the thousands taken care of. Now let's move over to our 300s. So now I need 300s. And I'm just going to draw a square and indicate that it's 100. 300, just like that. And just a word of a word of relief, hopefully a word of advice. You do not need to draw all of the little lines and all the tiny little squares and cubes on these blocks or these flats. And in fact, please don't. Don't draw all the tiny little lines, all the little division lines. You can, better yet, just write the number inside of it, just like I did right here, where I said, oh, that's 1,000. That's even better. Let me erase. Okay, so now where are we at? Oh yeah, so now we need to draw our 5 tens. And tens are easy. Tens are just lines. So we can say 1, 2, 3, 4, 5. Oops. Ah, that's the quantity 50. And then for the ones, you can just do dots. That's all you really need to do. 1, 2, 3, 4, 5, 6, 7. And there it is. And now notice specifically how I drew this representation. So this particular structure is very, very important because it's going to carry on into the next chapter, 3A. And in fact, lecture 3A, once we talk about it in just a moment here. Or in the next lecture, I should say. And the reason is because this is the perfect model that's going to lead them to be able to understand how these symbols work together. Because notice here, if I were to just kind of add a plus sign between all of these, and add all those up, then I would get the numeral 2357, which represents the number 2357. So this particular structure, the way that it's laid out is very, very important. The other thing I want to point out, because I know I had mentioned it on the activity rubric, is I'm not abusing the equal sign. Don't abuse the equal sign. So, and also don't abuse the plus sign and the minus sign. Don't abuse those symbols. Those symbols work for numbers, right? So don't put plus signs. I'm going to do this in red. Do not put plus signs in between these figures that you've drawn. Don't do that. That's going to mess people up. You can put them between numerals that you've written down, just like right over here. Plus, plus, plus. That's okay. That's okay. All right. Let's do another example just to see how it works. Let's erase this, and let's try a different number. What's a good number that we could try? What I want you to do is go ahead and think of your own favorite number for just a minute. Let's keep it in the thousands. Okay, I've got an idea. I'm going to do the quantity, oh, see a little thing up there. I'm going to do the quantity 4,293. 4,293. Now, I'm going to need 4 of those cubes. I'm being a little hasty here just to save time, but you should draw these with a little less haste if you have the time. Each one of these is representing 1,000, and this is going to be 4,000 right here. And then I need 2 hundreds. And then I need 9 tens. And then I need 3 ones. 1, 2, 3. Ta-da! And there it is. There's the representation, 4,293. And notice now that if you were to add all those together, you will get 4,293. Pretty cool, huh? Not too bad, right? If you want, I will do many and any more examples you would like. An interesting question is, what do you use when you want to go above 1,000? What are you going to use then? Interesting, huh? At that point, actually, we're going to talk a little bit about that when we go smaller, in fact. So I'll do that in a couple of slides. One last thing I wanted to note about these base 10 blocks is the vocabulary, because there's a question on the activity that asks you to use this vocabulary. So let me zoom in on this for just a moment here. This is the vocabulary that we use. You can't see it too well. It's getting cut off on the bottom, unfortunately. Oh, there we go. I can kind of zoom in. Um, for the tiny cube, we refer to that as the unit, or the one. We refer to 10 units as a long, and we refer to 100 units as a flat. One flat is 10 longs, and then 1,000 units is a block, the big block. So that's what we call a block. So just keep that in mind about that terminology. Okay, so this is actually a slide from the Smarter Balanced exam, the one that they give at the end of 3rd grade, and so we expect a 3rd grader to be able to answer this question. Let's take a look. It says Joanna has the following blocks: 2 hundreds, 16 tens, and 5 ones, right there. Lynn thinks that Joanna cannot model the quantity 342 with the blocks that she has. Click the blocks to show that Lynn is incorrect. So that's what we have to do. That's what we're asking this student to do. And you can kind of see. So if you want to just take a moment, pause and think about it, see if you can figure out what you would select. Okay, now let's do this one together. So first we need to model 300s. That's what we're looking for. We need 300s. And luckily, that's not too hard to see, right? Oops, sorry, 1 second. Pencil was acting up. Here we go. Here are here are 300s. There's this 100 here, one flat. Another flat gives us 200, and then we can highlight 10 tens, because 10 tens is 100. 10 longs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's the quantity 300. I've now highlighted the quantity 300 in pink, right there. Okay, so now we need to highlight, we need to highlight 4 tens. And we still have enough tens to do that. Let's go ahead and do that. 1, 2, 3, 4. Do that one better. 4, there we go. So now this is the quantity 40. I've now highlighted 40. And last but not least, we need to do the quantity 2. So let's see if we can find 2 ones. And we can. Here we go. 1, 2. And that's the quantity 2. There you go. And so altogether we have 342. And so this is what we would ask a 3rd grader to be able to do, which means they have a very robust understanding of their numeration system, the base 10 numeration system. And they understand how to use base 10 blocks. Remember the Common Core standard that was talking about representation, right? It's representation. Okay, so now let's talk about other bases. So if you're still struggling with those concepts, take some time to do a couple more examples on your own. I highly recommend it, because now we're going to move into other bases. We can group by tens, but there's no need to. We can group by any positive real number. You don't have to count by just powers of 10 or powers of 5. You can count by powers of any positive real number. So here are some examples. This is just the repeated structure. And this is where things get really trippy, right? So here is the quantity 123 written in base 10. Over here is the expanded representation, the expanded form, and it's exactly what we've been looking at this whole lecture so far. But then down here, this is how you write a different number, but it's the numeral 123, sorry. It's the numeral 123, and this little subscript is telling us that we're in base 5. So instead of grouping by powers of 10, we're grouping by powers of 5 instead. And here we go. This is telling us that we have one group of 5 squared, and then we have 2 groups of 5s, and then we have 3 1s left over. So let's go ahead and try to write that in base 10. Let's see what we have. Let me erase these for a minute here. Let's think about this. Okay, so how much is 1 times 5 squared? Well, 5 squared is 25. So that's 25. And then we've got 2 times 5. So that's 10. And then we have 3 1s, which is 3. So this is the quantity 38 written in base 10. And this is where it gets interesting. So remember, these symbols are just representations of the quantity. The quantity has not changed at all. This numeral, this set of numerals is describing the same quantity, the quantity that we call 38. Here's how you're used to writing it, because you're used to writing it in base 10. You would say 38 is 3 10s and 8 1s. Well, over here, what I'm saying is the quantity 38 is 125, 2 5s, and then 3 1s, which is exactly the same quantity, right? We're going to see another example of doing this with an actual just quantity on the next slide. But you can keep going in this way. So let's look at another one. Let's look at the next one. This is base 7. So one group of 7 squared, which is 49, two groups of 7, it's going to give us 14 after we add it up, and then 3 1s at the end. So let's see what we get. 49 plus 14 plus 3. Is that right? I think that's right. So what do we get here? That's 49 plus 17. That's 59 plus 7. That's 66 in base 10. So there you go. So where we would say, this is how we would write the quantity 66 in base 10. We would say there are 6 10s and 6 1s. But if we were in base 7, we would say there's one group of 49, there's two groups of 7, and then there's 3 1s left over at the end. Same quantity, different representation. That's it. That's it. Okay, and then lastly, if you want to really, really bend your brain, I'll just leave that right there. If you really, really want to bend your brain, take a look at this one right here. So that is 1, 2, 3 base pi. You can count by pies. You don't always want to. It might not be that meaningful, but you can. That's the whole point. You can. All right, so let's practice with this. Here is a quantity of objects, and we're just going to write this quantity in different bases. First, let's write it in base 10. That's super easy, right? Because here, let me do it like this. Here's one group of 10 objects, and then there are 7 left over. 1, 2, 3, 4, 5, 6, 7. So we would write this as 1, 7 in base 10. Sometimes we'll write the word 10 just to emphasize that just so it's not confusing. There you go. So that's 1, 7 base 10, or as we call it, 17. There you go. Let's do it in base 5. So if we're going to do it in base 5, then we need to think about powers of 5. Let's write down the powers of 5 first. Let's see, 5 to the 0 equals 1. 5 to the 1 equals 5. 5 squared equals 25. 5 cubed equals 120. Oops. Equals 125. And we can stop there. We've only got 17 objects. We can't even get 25 out of there. So we don't need to consider these two at all. We're going to start with these. How many 5s are there? How many groups of 5 can we get? Well, let's count them off. Let's see. Here's a group of 5. And here's a group of 5. And here's a group of 5. So we can get 3. There are 3 groups of 5. 3 groups of 5 to the 1. And then, now that we've taken care of this, how many 1s are there? How many 1s are left over? 1, 2. So there are 2 times 5 to the 0. So if we want to write this in base 5, we just look at the, oops, if we want to write this in base 5, we just look at these digits right here and spell them out. In fact, I'm going to write it like this. 3, 2, base 5. What is 17? It's 3 5s and 2 1s. Same thing. The quantity has not changed. The representation has changed. That's it. That's the big idea. Okay. Yeah, there you go. 3, 2, base 5. We did it. Okay, how about base 7? Well, let's count 7s again, right? Or let's look at the powers of 7 first. Let's write them out. 7 to the 0 is 1. 7 to the 1 is 7. 7 squared is 49. 7 cubed is actually 343. But again, we can stop there. We don't need to go that large for this problem. We don't even have 49 objects. So we don't care about cubes. We don't care about flats. And all that's left are these. So how many 7s can we get out of here? Let's pick them out. There's one. There's one group of 7. And then here's another group of 7 down here. So we can get 2 groups of 7. So 2 groups of 7. Now we've taken care of that. We've got to do the ones. How many ones are left? 1, 2, 3. So there are 3 groups of 1. So this number is written as 2, 3, base 7. And so that's how it goes. All right, there you go, 2, 3, base 7. Now let's do it one more time in base 2. So we got to look at powers of 2, and there's a lot more of those that we can, there's a lot more powers of 2 that are small. So let's go ahead and collect them. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. I'm just multiplying by 2 every time. 2 to the 6th is 64. 2 to the 7th is 128. And we could have stopped a long time ago, right? Let's see, we only have 17 objects here. So we can stop, we don't even need to consider any of these. We can start with groups of 16. So how many groups of 16 can we get out of this quantity? How many groups of 16? Well, there's one group right there. So we have one group of 2 to the 4th. Okay, now at this point you might be tempted to jump straight to the end and say that, oh, there's only one left, so it's 1 times 2 to the 0 and we're done. But you got to slow down, slow down. Remember, this is a place value system. You have to go in order. You have to go in consecutive descending order, right? You got to start with the biggest chunk that you can get out and then take smaller chunks down and down and down. If you can't take a chunk of the next size down, then you have to leave a placeholder there, the number that we call 0. So we have to go back and do that. So let's see. Yeah, so the next question is, how many 8s are there? How many 8s can we get out of this last one? The answer is 0. So we're going to add 0 groups of 8. Now, how many 4s can we get out? 0 again, right? So we're going to add 0 groups of 2 squared. And then now you can kind of see the game. Oop, that should be a times right here. Times. Plus 0 groups of 2 to the 1. And then now we're finally down to the ones. And so we're going to do one group of 2 to the 0. Trying to cram it in there. Let me just write it on the next line. Plus, better yet, over here. Plus 1 times 2 to the 0. So then we're just going to go through and collect those digits. 1, 0, 0, 0, 1. 1, 0, 0, 0, 1 in base 2. And congratulations, now you know how to write in binary. And you know how to convert back and forth. And that's what we're going to do in this class, converting back and forth between these things. But that's really all it is. So again, if you're struggling with this, come up with all sorts of examples. It's really great. Pick any quantity you want. Any quantity you want and try to write it in a different base. Just start chunking away things based on these powers. And that's all you're really doing, just taking things away in different powers, starting with the largest that you can get. Okay, oh yeah, so there you go. 10001 base 2. Okay, so if no subscript is used, we assume that it is in base 10. That's just because we're in a base 10 civilization here. So we use base 10, or a base 10 society. You can also talk about bases that are higher than 10. But if you're going to go higher than 10, then you have to come up with 12 new symbols. Or sorry, you have to come up with 12 symbols. And you can't use the symbol 1, 0 anymore to represent 10, because that's 2 places. That's 2 places. So if you want to be in base 12, you need new symbols to represent the quantities 10 and 11. And so usually what we do is we will use the letters A and B. So in this case, we're saying that A is equal to what we would write as 10 in base 10, and B is equal to 11 base 10. So that's what's going on here. That's what those 2 symbols mean. A and B mean 10 and 11. And so then what you can do is you can start writing down numbers like this, B3A. And at first it looks really funky. You're just like, wait, what's going on here? B3A? That doesn't make any sense. But that's okay. Just hold fast, because this is a place value system, and we've got placeholders there. symbols that are holding the place and telling us how many of that particular power we've got. So let's go ahead and go through and expand it out. This is saying we have B groups of 12 squared, because we're in base 12, plus 3 groups of 12 to the 1, plus A groups of 12 to the 0. That's what that means written in expanded form. So let me go ahead and emphasize that this is B, B, 3, 3, A, A. B groups of 12 squared, which is 144, 3 groups of 12, and then A groups of 1. Let's go ahead and calculate this. What does B represent in our system, our decimal system? It represents 11. So we're going to do 11 times 144. And then 3 times 12 is 36. And then A represents 10. So we're going to have 10 times 1. So I'll leave it at that. Okay, so let's see if we can add this all up. 11 times 144. Too hard for me. Let's just do 10 times 144. That's 1440. And then we need one more 144, which is 144. And then over here, we've got 46. Now, if you're not comfortable with going from here to here, which I don't expect you to be at all, that's good, because that's what we're going to learn in this class, because being able to do that type of calculation in your head is much simpler than you might imagine, and much simpler than you may have been taught in the past. Okay, so now let me go ahead and combine some more things. 1440 plus, let's see, what is that, 190? Let's see, 144 plus 46 is 150 plus 40, which is 190. Now, 1,440 plus 100 is 1,540. And then we're going to have, what is that? 1630. 1630. 10 less than adding 100 more. So that's what it looks like in base 10. That's the idea. So the quantity B3A is the same as the quantity 1,630 in base 10 in the decimal system. And that's it. So you might even be able to tell there's some advantage in this case, right? Because we were able to write what was a 4-digit number as a 3-digit number up here. So that's kind of handy. Okay, let's double check. Yeah, there we go. We did it right, 1630. Okay, there's also some popular other bases like base 16, which is called hexadecimal, and base 2. Those get used a lot in computer science. And one of the nice things about binary is that it's only got zeros and ones. So binary only uses the digits 0 and 1, which is nice because the one thing that we can really do with electricity is turn it on and turn it off, on and off, on and off. And so what your computer does is it literally takes those pulses in electricity and filters them through some other little like microchips and then spits out what you're looking at right now, your computer screen. It's pretty amazing. Oh, or if you look at a power button, look at the power button on your computer or on like on lots of things, and you might notice that the switch has a 1 and a 0 on it. That's what it means, because it's the power on and off. Or sometimes they use this little symbol right here. That's a 1 and a 0. Pretty cool, huh? I think that's cool. Okay, so binary is also fun because I think once you can see how to count in binary, it helps you see how to count in other bases. So I want to go to this counting in binary video that I've got. If you want to look at it again on your own time, you can just click this link and it'll take you to it and you can watch it again. But let's pull it up right here and let's watch it together. Okay, so we're just going to count in binary, and you can see that we've got a bunch of places, and all the places are filled with zeros to start because we're starting at 0. And then we're just going to count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Notice that we actually just calculated that that was 17, right? Flip it more, 18, 19, 20, 21, and it keeps going. Oh, looks like it just disappeared on me. One second, let me open that up again. Pause. come back here. I'm back here. Okay, there we go. But yeah, so that's the idea. So I think once you can realize what's happening right here, that's the key point. Because the idea here is that that symbol, 1, 0, does not always represent the number 10. Doesn't always represent the number 10. You might think it does because you were raised on the decimal system, right? But it can represent whatever we want it to. We just have to think about what base we're in. So I encourage you to watch that a few times. I think it's really helpful. And we're going to count in a different base right now. Let's go back to the slides for a minute. Let's try counting in base 5. I think once you count in base 5, it can help to really clear things up. So check this out. We're going to count in base 5. We're going to go 1, 2, 3, 4. But once we get to 4, if we add another one, we have a group of 5. So we wouldn't write 5, we would say one group of 5 and 0 things left over. 1, 0. One group of 5, 0 ones. One group of 5, 1, 1. One group of 5, 2 ones. One group of 5, 3 ones. One group of 5, 4 ones. Now we're going to get another group of 5 if we add another 1. So it'll be 2, 0. 2, 0 is the quantity 10 written in base 5 because we're saying you've got two groups of 5 and 0 ones left over. Let's keep going, shall we? So, okay, two groups of 5 and then 1 left over. 2, 2, 2, 3, 2, 4. Now we're about to get another group of 5. So we'll write 3, 0. And we can proceed. 3, 1, 3, 2, 3, 3, 3, 4, 4, 0. There it is. And then we can keep going. 4, 1, 4, 2, 4, 3, 4, 4. Now we're going to get another group of 5. But if I'm going to have a group of 5, that's going to give me another group of 5 over here. But then I'm going to have 5 groups of 5. And if I've got 5 groups of 5, I wouldn't write it like that. I would just say I've got one group of 25. And that's exactly what I'm going to do here. So we're going to go 1, 0, 0. One group of 25, 0 groups of 5 after that, and then 0 ones left over. And then you can proceed. 1, 0, 1, 1, 0, 2, 1, 0, 3, 1, 0, 4, 1, 1, 0, and so on. So I encourage you to try that a couple times too, and I think that'll make things click really well. Okay, now where are we? Oh yeah, so the other nice thing about this is that basimal systems, we're almost done here, I promise. I know this is a long lecture, but it's an important one. Basimal numeration systems, meaning it doesn't matter what base you're in, as long as it's some base, they extend naturally to fractional quantities. And we actually saw this in base 10, and in base 10, it's almost natural for us, right? Let's look at an example in base 10. So here, we're looking at the quantity 78.367. And if we write it in expanded form, notice how the form just continues perfectly, right? Look, we've got 7 tens. We've got 8, actually, sorry, I should say this. 7, let me get my colors here. There we go. We have 7 tens. And then we have 8 ones right here. There's our 8 ones. And then the next step is where it gets interesting because that's in the tenths place. But how do you write a tenth as a fraction? Or how do you write a tenth, how do you write a tenth as a power of 10? Well, like this, 10 to the negative 1. Remember, if you have a negative exponent, it drops that number into the denominator and makes the exponent positive. So what I'm getting at here is that 10 to the negative 1 is equal to 1/10, or 1 over 10 to the 1. Same thing here, 10 to the negative 2, that's 1 over 100, which is 1 over 10 squared. So as we proceed like this. Here's our 3/10. Let me just emphasize this right here, actually. Oops, come here. There you go. These are our 3/10 right there. I've got 3/10, and then over here I've got my 600ths, and then down here I've got my 7,000ths. And then you add all of those things up. You add 70 and 8 and 3/10 and 600ths and 7,000ths, and then you get 78.367. That's the idea. So it extends very naturally, right? It's almost like it's just so beautiful that this numeration system works so well. But the thing is, it doesn't have to be that way, or I'm sorry, it doesn't work that way in only base 10. Let's look at a different base. Let's look at this example in base 2. So in base 2, we've got this number right here on the left, 1011.1010101. So following the repeated structure that we saw before, let's check it out. We've got one group of 2 cubed, 0 groups of 2 squared, one group of 2, and one group of 1. Now we're on the other side of the radix. Notice I don't call it a decimal point now because it's not a decimal point. I guess you could call it like a binary point if you want. But then people are going to be like, what? Well, people will be like, what anyway, if you call it a radix, but you know what I mean. Then we're going to have one group of what? Well, it's not going to be 10 to the negative 1. It's going to be 2 to the negative 1. And 2 to the negative 1 is a half. 2 to the negative 1 is a half. So we've got 1 half. Then we have 0 groups of 2 to the negative 2. And what's 2 to the negative 2? That's a fourth. So we have 0 groups of 1/4. Actually, let me write that up here. 1/4. And then here is 1 half. 1 half. Okay, so where were we? Okay, so now we've got one group of 2 to the negative 3, which is 1/8. And then 0 16ths and 1 32nd. And so you can kind of see those all translate down here. One group of 8, one group of 2, one group of 1. Here's our 1 half coming from right here. There are no quarters, so that's gone entirely. And then you've got our 1/8 coming in right here next to it. And then we've got our 1/32 coming in from over here because this disappears also. And there it is. So then you can add all these things up. You add these up and you get 11. You add these up and you get 21/32. And so this quantity is the quantity 11 and 21/32 in base 10. In base 10. So that's how we convert from base 2 to base 10 in this case. There you go. Pretty cool, I think, huh? Okay, so you're going to get lots of practice with this on the WebAssign and a little bit of practice on the activity. Yes, okay, that's the end of this lecture. Let's take a look at the activity before we head out. Thanks for bearing with this, this particularly long lecture. Okay, so let's go to the activity here. Activity 2A. Here we go. Once again, getting ahead of myself. Delete these things here. Delete. Delete. There we go. Okay, so let's take a look at this activity, activity 2A. The first question is just asking you to draw base 10 blocks representing that number. Pretty straightforward, not too bad. This question is asking you to use the terminology associated with base 10 blocks. So essentially translate this sentence here that you see into an equivalent sentence using the terminology of units, longs, flats, and blocks. This one you're going to show why 1,234 is not the same as 1,324 using base 10 blocks. And all you have to do is draw the two different representations, and you'll be able to physically see why they're different. Represent 99 with base 10 blocks, and then illustrate the act of adding 1 to 99 and the appropriate regrouping that results. So this question is actually a lead-in to the next chapter, chapter 3 and lecture 3A, in fact. What you're going to do is you're going to first draw a picture of the quantity 99 represented with base 10 blocks. Then you're going to try to draw the act of adding a single unit. And then you're going to have to draw another picture, I should go this way, draw another picture that shows the regrouping, what happened after you added that. And that's why you can use all this space. So that's what you're going to do. And then we're going to do more of that in the next chapter. And then problem number 5 is converting back and forth between bases. Back and forth between bases, just a bunch. Notice that there are some that are in larger bases and some that are fractional. So you do need to practice that. Last note about this problem here, or this last question. This is a challenge. If you don't finish it, that's okay, but I encourage you to try it because it's a challenge. Um, and it will really, if you can do that problem, you'll fully grasp different bases and numeration systems, guaranteed, if you can make sense of that problem. Um, the last bit I wanted to say is that the process from converting between base other to base 10 is not the same as converting from base 10 to another base. So don't lock yourself into procedural mathematics, right? You got to think about the problem, make sense of the problem. You're not just regurgitating a procedure. So beware when you do these particular problems. And again, feel free, ask questions at any time, and we will answer them all together. Okay, so I think that's enough lecturing for today. Once again, thank you for bearing with me, and I will see you next time.